Chapter 24 talks about diffraction, interference, and then we go to polarization. So all this comes under wave nature of light. Okay? So chapter 24 is all about this. If you know the concepts of diffraction, interference, and polarization. So what we did in the previous chapters is reflection, refraction, dispersion, right? Reflection of waves, refraction, dispersion, and then total internal reflection, and all those things. Now, this is diffraction. So what is the main idea behind diffraction? Diffraction is a spreading of light when it passes through a gap. When light passes through a gap, the light spreads. And that spreading action is called diffraction. So, spreading of light as it passes through an aperture. Aperture or gap. Now, this spreading of light cannot be explained without the wave theory. So what is this wave theory? It's Huygens wave theory. Huygens explained how waves actually travel, okay, from a source. And you know that from a source, they travel in the form of wavefronts. What's it called? Wavefronts. What's the space between wavefronts? Lambda. And Huygens explained how each wavefront is constructed. Basically, each one is a constructed wavefront. So, if you're looking at this wavefront, each point on this wavefront acts as secondary sources of new waves. So each one is going to act as new source. So this one is going to spread the waves there, this one is going to spread the waves. So every particle, every point on the previous wavefront is going to send waves around it. So if you join all the extremities of the waves that are going on, you get the newly constructed wavefront. Make sense? So understand that even the newly constructed wavefront is made up of points which will produce new waves, and the new waves keep going, and that forms a new wavefront. So each line that you draw is actually a wavefront, which is a constructed one out of the little ones. So Huygens' main idea is this, that each wavefront acts as a source of miniature secondary waves, and the locus of all the points connecting the secondary wavelets gives you the new wavefront. So this is how Huygens explained this, and that is what is needed to explain all these things. So let's see how we can look into Huygens wave theory and how Huygens theory helps us to study better. All right. If you're looking at waves, light as rays like this, if you look at light as rays, and suppose you have a gap like that. Suppose you have a gap. What will happen to this ray? It will just bounce back. What will happen to this one? It bounces back, bounces back. This one passes through, that one passes through, and this bounces back, that bounces back. So what you should see on a screen kept anywhere is basically these that are going to hit. So if this slit is 5 millimeters, then you'll have 5 millimeters of light, right? It just produces exactly the same shadow. That's what a ray model will help you to understand. But a wave model really helps you to understand what exactly is happening. It is spreading. It doesn't go like this. It spreads. So after it passes through the gap, it spreads. So how does it spread? How does hygiene explain the spreading action? Is what comes next. So leaving the ray model aside, now let's look at the wave model. So let's take plane waves. So these are plane waves. Now, what are these plane waves? Plane waves are waves that are coming from infinity, that are coming from far away. Okay? Plane waves are waves that have originated from infinity, like sunlight. You can pretty much consider the sun to be at infinite distance because it is pretty far away. And so the sun's waves that are arriving here are nearly plane. Nearly plane, not 100% plane, right? It's nearly plane. So, how are these wavefronts constructed? Each wavefront is constructed, so each and every point over here acts as new sources, and so it will send wavelets and join all the wavelets. You get a new wavefront, and that same story applies here. What happens when it comes to the edges? What happens when it comes to the edge here is these waves which are hitting the material part of this slit bounces back. This one bounces back. Now let's look at the waves right in the middle here. All these points act as new sources. So what will happen is these sources will send the waves in this direction here. It's sending it. This one sends it. That one sends it in the same direction. But the ones which are at the end, they won't just stop like that. They also will send the waves. So there will be a little bit of a spreading action right there, the edges. And the same way here. So eventually what will happen is you'll get a wave that goes like this. And this is a new wavefront, which is not completely plane. And what will happen is this spreads exactly the same way. And so on. So what you see on the screen is a spreading action. So instead of forming a geometric shadow of the slit, not a shadow but the opposite of a shadow, instead of forming a geometric shadow here of light, you are actually able to see light all over the place. And that is spreading of light as it passes through an aperture. And why is it spreading? Because the waves that are originating from here, they have the freedom to go to the sides as well. Make sense? Like if students are running out of the door, and this is the tunnel kind of thing, so everyone is like organized and running along with this. But as soon as you cross the door, you're not going to keep running straight, right? There's more freedom. So you'll automatically kind of spread out from there. And that is diffraction. Diffraction is the spreading of light as it passes through a gap. Now let's look at it more geometrically. What causes spreading? To what extent will it spread? Will it spread only till here, or here, or here? Right? That is what we're going to see now. So, till where will it spread generally? So we have the slit. I'm just magnifying it so that you can see it pretty well. All right. Remember, these slits are supposed to be extremely small, fractions of millimeters. But I'm just showing it bigger so that you can understand. And the screen is there. So when waves come from here, all these are going to be sources of the waves. Now here is our screen. The screen is placed there. Since waves are coming from all these places, all these waves are going to move on, and right in the middle here, that's going to be bright. Why is it bright? All these, majority of these waves, they go and hit here constructively. You know what's constructive interference from last year? Yeah. Constructive interference when the two waves are kind of together, they build up. So most of these waves from here, they kind of build up and create a central brightness. It creates a central brightness or central maxima. Central maxima or central brightness. That's what happens there. Now, what happens on either side of the central maxima? So what happens here is, with reference to the middle of the slit, something that's going and hitting here. So if a wave is going till here, and if a wave from here arrives there, and if the path difference between these two is half a lambda, what kind of interference can be expected? If the path difference is half a lambda, destructive. Remember from last year. So what do you mean by path difference of half a lambda? It's like this, so I'm just showing it here. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 waves. 6 wavelengths. And here, 1, 2, 3, 4, 5, 6. 6.5. See the way it is hitting here. The crest is coming and hitting the trough, right? So what is the path difference between those two? It's a half a wavelength. And the half wavelength is what causes this to be not dark, but minimum. Why is it not 100% dark? It's not 100% dark because we are looking at this and this. What about the other points? There are waves arriving from other points to the same area. They could be constructive. So from other places, you can have some intensity coming here, which means it won't be 100% dark. It will be majority dark. And that is why we call it a minimum. That means the intensity is not zero there. It has got some intensity. Make sense? Central brightness is really bright, but this is minimum intensity. Minima. It's not dark, it is like light. And this happens on either side, okay? This happens on this side also. Now, if I look at this geometrically, if I'm going to look at this angle as theta, this one is theta. The angle at which it happened, if it is theta. If I drop a perpendicular from here, approximate perpendicular. Look at this figure here. If this angle is theta, this angle is theta as well. And if the distance of the gap, the slit, is A, right? A is the gap. We call it slit width. A is a slit width. If that is slit width A, what is this? A over 2. What is this? Lambda over 2. Why? Because the path difference is supposed to be lambda over 2 if you want to have destructive interference here, right? The path difference between these two waves should be lambda over 2 if you want to have majority destructive. Therefore, this is lambda over 2. Now look at this little triangle that you see here. What is the trigonometric connection between theta and this and this? Sine theta is equal to lambda over 2 divided by, which implies that sine theta is equal to lambda over a. This is an important equation for diffraction. Sine theta is equal to lambda over a. And what is lambda? Lambda is a wavelength. And what is a? A is a slit width. And what is lambda? Lambda is the wavelength, which is basically this. That's a wavelength. Lambda is a wavelength, which is from here. Right? These are the wavelengths. Lambda is a wavelength, and A is the slit width. Now, what is theta? Theta is the angle at which you have the first minimum. The first minimum. So the condition for this to happen is sine theta is A sine theta is equal to lambda. A sine theta is equal to lambda. That's a condition for that particular position. So since this is called a minima, what does a minima mean? Majority of the waves from here are meeting here destructively. And there are some minorities which are constructive, right? Which implies that if you go this way or that way, it's going to get brighter. Because it's a minimum. So the intensity is maximum over here, and it goes to a minimum over here. When you say minimum, if you go here, it should be higher. Otherwise, how can this be a minimum? So as you go and search in this area, you will find more brightness than this. Why? Because then the majority of these are more constructive, not fully destructive. So you'll find brightness again here. And then, if you keep looking around, you'll find a place where you have next minima coming in. And that's a second minima. And the condition for that will be A sine theta is equal to 2 lambda. A sine theta is equal to 2 lambda. That's going to be the second minima. And if you keep looking around, you'll get the third minima. This happens on either side, okay? So what I'm trying to say is the amplitude or the intensity is maximum over here, maximum intensity over here, and then goes to a minimum intensity over here. And then after that, again it goes up, and again at the minima, see? And then again it goes up, and again a minima. Keeps going like that. That's the brightest. First minima. Secondary maxima. That's called a secondary maxima. Secondary maxima. This is central maxima. That's a secondary maxima. That's a second minima. Third minima. Fourth minima. And what happens is the intensity keeps dropping. Why is the intensity dropping? Because you're going far away from the source. So if you put the screen's intensity will be highest right there, goes down, and then the intensity goes like this, like that. The further away you go, intensity becomes weaker and weaker, yes.
Is the secondary maximum anywhere close to the actual maximum?
No, it's far below. Actual maximum will be super bright. And then this intensity is, this is there because a little more than, majority will be more constructive. But you know what intensity, intensity equation from last year, you've done intensity is equal to power over 4 pi r squared. Remember this equation? Intensity is power over 4 pi r squared. So the further away you go, intensity becomes weak. So that's why the further away from the slit you go, it gets weaker and weaker. You can see the intensity is falling off. And this happens on both sides. That happens on both sides. So this is almost like an intensity graph. As you can see here, this is your axis. That's your axis. That's the intensity. That's the intensity. So try to flip this like this, and you'll be able to understand that, right? So that's the y-axis, and that's your x-axis. And you can see the intensity is highest here, minimum, second minimum, third minimum, fourth minimum, on either side. Okay. So this is the idea of diffraction. Yes.
That kind of looks like the sine of x divided by x graph. It's on the side.
Which one is that?
Sine of x divided by x.
Which graph are you referring to?
The red line.
The whole thing?
Yeah.
The whole red line.
The whole thing?
Yeah,
Consider
if you
this as the y-axis, you mean?
No, if you made that
That's-
the x-axis.
Oh, that is the x-axis? Sine x divided by x. And what is the y-axis?
The
Like, I guess
Oh, no, this is your y-axis.
no, that's the nose. The
If you took that as the x-axis.
and the,
So, in other words, you flip it like that?
yes, and the central brightness is where zero is.
So, that's a 0.
Yes.
And what is this axis?
That's the y.
That's a y. And that is theta? Or x?
Yes. And that's x.
Oh, so you're plotting with respect to x. Okay, so
Yes.
yeah,
Like,
I don't know exactly the shape of the graph. Is that what it is?
if you come,
But I don't think we would pass them.
it's the same pattern. So like in the middle, it's at its like highest peak,
I
and
got
then
it.
out on the
So
side.
it's kind of going down.
Yeah, it keeps going down.
I mean, it goes below. This one doesn't go below.
Right. So it'd be like a vertical shift of the graph, but like,
Vertical shift, but
it's
this
the
is
same pattern.
this is even.
Yes, it's even on both sides, and
This
like
is not
this
even.
is its highest peak. Oh, it's not even. Oh.
Yeah, this is a slightly different thing. These get crowded up as they go on. Because sine is not, it's not like proportion. Now, if lambda, look for, at this example. Suppose this is 10 centimeters wavelength, and if the A is 20 centimeters from here to here, what's going to be the angle at which you get the first minimum? Check it out. Check it out. If this is 10 centimeters wavelength, and if A is 20 centimeters, what's going to be the angle? 30 degrees. Pretty much like in the diagram. It's not 30, but it's more than 30. Yeah, 30 degrees. If lambda is 10, and this is 20, 10 over 20 is 0.5. Sine inverse of 0.5 is 30 degrees, right? So you'll see a diffraction. So what is the requirement for seeing a diffraction? Number one, you should have a single wavelength. One wavelength. You can't have like white light. With white light, it will be all confusing because all of them are different wavelengths, right? So the light should be monochromatic. Monochromatic. Which means single color. Which means single wavelength. Monochromatic means single wavelength. So it should be single wavelength. And what's the other condition required for you to see diffraction? The A should be very comparable to lambda, like close. What if the A is too big? Like this window. Take the window as a slit. Take the whole window as a slit, right? And think of white light is average color of 600 nanometers. So the wavelength of white light is 600 nanometers approximately, and the slit is 1 meter long, wide. So this is 600 nanometers, and that's 1 meter. What do you think is the angle? Literally nothing. And that's the reason why you must have seen sunlight coming from the window and just casting its brightness on the wall. Do you see spreading? Not at all. You just see like that block. So if you measure the window's width and the brightness on the wall, it will be same length. It should be same because the rays are coming together. Make sense? So why this window is not causing diffraction? Answer is the A is too big. So the angle theta is negligibly small. Get it? The angle theta is negligibly small, so you will not see any appreciable diffraction. So if you want to see appreciable diffraction, you need this A to be pretty small. Okay? Diffraction studies of crystals are done based on this idea. Why crystals can cause diffraction? In fact, the crystalline structures are studied through this experiment called diffraction. You shine light of one color into a crystal, and the crystal has lattice spacing of atoms, right? And those spacings act like this. The lattice spacings act as if they are like gaps. And when the light passes through, they just spread. And the angle at which it spreads can be actually measured on a screen. And then you can actually figure out A, because you can measure the angle, and you know the wavelength of light you use in the crystal. So you can figure out what exactly is the atomic spacing. That's called diffraction studies. Okay? And in diffraction studies, they don't use light. Why? Light's wavelength is too big. So what do they use?
Radiation.
Like what?
X-ray.
X-rays. X-ray diffraction studies. It's called X-ray diffraction studies or gamma ray diffraction studies. So basically you shoot gamma rays into the crystal and then study it. Why? Because the A is too small. So you need them to be comparable, like close. Make sense? So why this window is not casting this kind of intensity pattern is because it's too big. Now if I want to really demonstrate diffraction, what do I need? I have a laser which is 750 nanometers, but I need a gap which is pretty small. So if I have a gap which is very small, I may be able to show diffraction. And you must be able to see this on the screen. Now how much it spreads depends. Okay, what if lambda and A are equal to each other? Suppose this wavelength and the slit is that same width. What is the angle at which the first minima should appear? Yes, either? 90 degrees, which means what? The first minima has to happen here. So what do you think is going to happen on the screen? It's fully bright. The screen will be fully lit. Make sense? So the intensity pattern, this is called, this line is called diffraction envelope. That pattern, the amount of spreading that takes place is called diffraction envelope. Like that. Why is the diffraction envelope going down in intensity as it goes on further and further? Because the intensity of light fades off with distance, right? Why do you see minimas in between? Because majority of these rays meet here destructively. That's why. And majority of them meet here constructively. And the condition for this first minima is A sine theta is lambda. Condition for second minima is A sine theta is 2 lambda. Condition for the third one is A sine theta is 3 lambda. Condition for the nth one is A sine theta is equal to n lambda. That's the condition. So how many of them can you see on a screen depends on these numbers. If A is equal to lambda, theta becomes 90. If A is equal to lambda, theta is equal to 90 degrees. Which means the entire screen will be illuminated, which means what? This envelope will be stretched all the way. Make sense? So this will be spread like this all the way. You won't see the first minima at all on the screen. Okay? Now to demonstrate this, I have I've got a bunch of slits here. Now you can see the slit which is bigger. Can you see that slit?
Yeah.
That's a big one. Maybe 2 millimeters, something like that. And then it goes thinner and thinner and thinner, and then finally a tiny scratch. I'll show how this laser is monochromatic, one wavelength. And that's A, the gap. So if I shoot light through the top one, you hardly see any diffraction. Because the top one's A is big. Let's say it's 2 millimeters. So if it is 2 millimeters and 750 nanometers, can you find out? If it is 2 millimeters, if this is 2 millimeters and this is 750 nanometers, calculate theta. How many degrees? (750 nanometers) and 2 millimeters, 0.002 meters. What is the angle coming out? Should be very small. 0.00 something. Oh,
0.02.
0.02?
Yeah.
So 0.02 degrees. Hardly there. Which means if I shoot light through the top one, it literally goes there and you don't see any more intensity variations. But as I move down to the smaller ones, when you go down here, the angle will be significantly, sufficient enough to spread out the light. And I'll show that right now.
It is.
Sean, can you take a picture of what is going to be on the screen and send it to my wherever?
Should we turn off the lights? Or?
Yeah, you'll turn off the lights. So
That over there?
yeah.
Okay.
So okay. Now you can go closer if you want to take it better. Now this is from the top. Cool.
Thanks.
You can go closer there.
Do you want me to just like directly under it or something?
Yeah, straight there. Now that is. Oh, wait.
I guess.
That's a top. That's a topmost one, and you can see kind of spreading and all that. That is not really a diffraction thing. It's just a kind of internal reflections from the glass. That is not much. Just take picture only, not video.
Oh yeah, I see.
Okay, I'm going to the next gap. The next gap is a little more thinner. You do see a little bit of extra spreading. Yes? I'm going to go thinner than that.
No.
I don't know if I'm pointing the right thing. Yeah, that one. Let me go to the right bottom because the other ones are too wide to cause any significant. Okay, I'll go to the very bottom. What's happening in the world? Okay. Yeah, I think I put it in this.
Wait, what?
There's a lot of. Yeah, do you see that one now?
Yes.
Forget about the other glare that you see on both sides. That is just some optical disturbance. But wait, I lost it. Yeah. Do you see central brightness? And then after that it becomes minima, and then again it becomes a maxima, and then again minima, maxima, minima, maxima, minima, maxima. You can see a little bit of it, at least 5 minimums you can see, and after that you don't see any more, right?
So the minimums, they basically don't even look like there's anything
Yeah,
there.
because the reason is the background illumination on the sides are literally close to the brightness of the. There's no contrast. That's basically the reason. In fact, the minimum maximum is supposed to go all the way around. It's supposed to go all the way around. But the contrast between the minima and maxima kind of fades off. And after that, you don't see anything more. Right? Do you see that?
Mr. CM, can you wiggle the normal laser pointer around for a while? Like the normal one without any of the, without going through any of the slits?
Anything?
Yeah, like that. Can you wiggle that around for a second?
Move it around?
Yeah, like that. I think
Why?
I did a live photo.
Is it kind of...
I want to see if I can turn it into one of those effects. I wonder they have a
What effect is that?
something called long exposure that just combines everything.
Oh, okay.
Like
It just kind of...
combines them all into one. But I got this funny.
Oh, you get almost a line?
Yeah, earlier.
Oh, so I need to do like that.
Yeah, and then it shows up. Like I got one that's this J.
Wow!
Yeah. I just got a J.
Whoa, what is that?
Sean, can you share with the class?
Yeah. I just J.
You're trying to write my name there. So, did I do that actually?
I think I just took a photo while you were wiggling it around like that. It's
Wow.
a pretty nice J.
That's a pretty cool J. But look at that. I don't know how it is done.
Awesome.
Okay. So, did you see the diffraction part of it?
Yes.
Yes.
A little bit. Let me see if I can show it here on this screen, on this wall. I don't know why this extra glare is coming through. All those little dots that you see there are because the glass just now it actually kind of broke, sort of. So I think that must be the reason why it is kind of scattered. But on a distance. Oh, that's much better. Oh. Take that picture. I think this is better.
What is it up against the wall?
Yeah. Where's it gone? Lost it?
Oh.
I think it's better. That one. Alright, so central brightness and the minimas on both sides, and that's what pretty much you see. Now, okay, turn the lights on, thank you. Good. So, I was shining light through the top one first, and then through the very bottom. No matter. Yeah, there's a breakage. That's why it was kind of. Yeah. So, how far do you think that first minima appeared on the wall? Like that much? Say 5 centimeters? Yeah, it was like 5 centimeters, that much. On the wall. So, let's say that was 5 centimeters. And this from here to here is 5 meters. What do you think is the angle then? Calculate. If that was 5 centimeters on the wall, and that is 500 centimeters from here to the screen, how much is the angle? What do you do? Tangent, yeah. Tangent of theta is 5 over 500, which is 0.01. So what is tan inverse of 0.01?
0.572.
0.572 degrees. Now use that equation and find out that scratch. Use this equation now. You can use this equation. Sine of, what is that point?
0.573 rounded.
0.573. Sine of this much is equal to lambda 750 nanometers over A. What is A? That is the actual thickness of the line, the width. You should be able to get that. So by the looks of it, it should be less than a millimeter. Less than 0.1 millimeter. It looks like it's less than 0.1 millimeter, 1/10 of a millimeter. Do you see the scratch from there?
Yeah.
It's a tiny, tiny, tiny scratch at the bottom.
Minus 7.5 times 10 to the negative fifth.
That's what I got.
Say it again.
7.5 times 10 to the negative fifth. What do you get?
Is your calculator in the degree mode?
Yeah, it's in degree mode. Sine of 0.573 is 0.01.
Oh, meters. Yeah, you may be right. Yes. Yes, you're right. What is it, 7.5?
7.5, yeah, and then I have 10 to the negative 5.
Minus 5.
Yeah.
Which means 7.5 times 10 power negative 2 millimeters. Which means 0.075 millimeters. That's why I said it's less than 0.1 millimeter. So you're right. So that scratch is only that much. Now think this is the atomic spacing. So this is exactly how they do studies. If that is the atomic spacing, how do they find out that atomic lattice spacing of between atomic layers? They'll find where the minima happens. They'll know this. They can figure out the theta, use this equation, find out the age. Okay. Any questions on this? Good. So that is called the diffraction envelope, and this is what happens when you have a single slit such as this. So I can write this down: diffraction, single slit. This is single slit. It's called single slit diffraction. Single slit diffraction. Now, interference. Interference. Yeah, the double slit experiment. It's also called Young's double slit experiment. There's the person who actually Young's double slit experiment. So let's see what happens when you have two slits. So here's a slit. The width is A. The width is A. And the separation between the slits, the opaque part of it, is B. Okay. So since you have two slits, and if you keep a common source here, these two slits behave as two sources, S1 and S2. And what kind of sources are they? What's the word for it? Coherent sources, right. So S1 and S2 behave as coherent sources, which means they have the same wavelength, they are approximately same amplitude, and they are in phase or have a constant phase. So when these two slits are illuminated, on the screen, kept a distance d away, you're definitely going to see the consequences of light starting from S1 and S2 on the screen. So what is this slit? Suppose I cover up the slit. If this slit alone is open, what is going to be there on the screen? If only one slit is open, the other one is like closed. Only one is open. What do you see on the screen?
It would just be like the same as a single slit.
Single slit, which is diffraction, right? So you're going to see intensity variations on the screen.
Mr. Sam?
Yes.
Dr. Stu just wanted me to remind you to put those grades in from like the silence.
Oh, yours?
Yeah. Just at some point.
I know.
Yeah, it should be done soon.
English, stats, and
All right,
yeah.
come back to this. When only one slit is open and the other one is closed, you will see a diffraction envelope on the screen, which means you will have this region is brightest. So it'll be bright over here, and then the intensity kind of varies like that. Brightest here, and the intensity variation is like right? So that is what you see on the screen. That's what you see on the screen. The middle, it'll be bright, and the diffraction allows less light to come over here, and then more light to come back again here, and then again less light. So this is the minima for diffraction. This is another second minima for diffraction. This is a central maxima for diffraction, right? What is the condition for this to happen? What's the condition for that to appear? Like, what is the diffraction condition? A sine theta is equal to 0, right? When A sine theta is equal to 0, you get there. That's maximum. And what is the condition for this? A sine theta is equal to the wavelength, 1 lambda. So A sine theta is 1 lambda, gets you a minima, the first minima. The second minima is A sine theta is equal to 2 lambda, which means the secondary maxima of diffraction is between them. A sine theta is 1.5 lambda, right, and goes on. So how many of them do you see there? Depends on the A and the wavelength of light and all that. So this is what you see on the screen if one slit is eliminated. Only one. If only this is open, but this is closed, you will pretty much see the same thing there, because these are very close together. These are really close together. So they are so close together, you cannot just differentiate them. So you will see the same diffraction envelope, which means more light here, less light here, little more light here, less light here, and that fluctuation, you saw that last class, right? When both are left open, then comes the interference. So the light from this source and from this source, they both go and strike, and according to the condition for constructive interference and destructive interference, they'll meet there constructively or destructively. So from here to here, you may have a bright band. Is that for me? That's strange. That's weird. That's a bright band. Why is it bright? Because these two light sources travel exact same distance, and so there's no path difference. There's no physical path difference between these two. That's why it's bright. Now, if that is bright in the center, what if you kind of look in this area? In that area, it's possibly dark. Why? Because this little spacing that you see here, that might correspond to half a wavelength. If that corresponds to half a wavelength, you're going to get a dark. even though diffraction allows light to come here, interference kind of does not allow the light to come there. Interference does not let light to come there. It's making it dark. Because what's the path difference? What's the path difference? Half a lambda. The path difference between the two waves arriving there is half a wavelength. That's why it's destructive. What if the path difference is 1 lambda? It's going to be bright again. But is this brightness as bright as this one? No. Why is this less bright? Because diffraction only allows this much. The diffraction is only throwing this much intensity on the screen, and so if it is bright because of interference, it's going to be only that much bright. Make sense? And this is dark in spite of the fact that diffraction throws light to the screen. Diffraction makes, the interference makes this one dark, which means you don't see anything at all there. It's dark. And this goes on. This is going to be dark, that's going to be bright, but this is bright over here according to interference, but diffraction is not showing much light there. So what is going to happen is this bright is going to be very dim. Make sense? What's going to happen after that? You're going to have dark, and then again bright, but this bright is really bright. Compared to this bright is really bright. Why is it bright again? Is because now it falls in the second peak. So diffraction is letting more light to appear here, and therefore the brightness that is formed over there is bright enough. And so it keeps going dark, bright, it goes like that. Okay, what is the path difference required for the central bright band? What's the path difference? 0? The central one is actually formed by 0 path difference, right? Here, that's a path difference. A sine theta is the path difference. What is this one formed by? Well, this is A sine theta 0 for the diffraction. For the interference, it's not A but A plus B, because what's the gap between the two slits? The gap between the two slits is A plus B. The gap between the two slits is A plus B. Make sense? So when light goes from here and hits here like this, what should be the path difference between these two? Obviously this is traveling extra path. What should be the path difference between these two in order to make it bright again? 1 lambda, right? So if you look at the if you look at that angle theta, this is 1 lambda, and that is A plus B. So look at the trigonometric ratio there. Sine theta is equal to 1 lambda divided by A plus B. So sine theta is equal to lambda over A plus B. That is what makes this bright. Yeah.
Wait, what is the diagonal line?
It's kind of a perpendicular line drawn to split these up. So just to try and find out how much is the difference in length between those two. Now, since they are so close together, drawing a perpendicular is almost like cutting off equal lengths. Because they're close together. If it's like as far as this, definitely this is not equal to this. Right? Because that's the hypotenuse and that's the adjacent side, so it's definitely not equal. But if these two are so close, drawing a perpendicular, like they're so close, like if this is what you're looking at, one going from there and one going from here, if you drop a perpendicular like that, these two are literally the same. If the angle is small, the hypotenuse and adjacent side will almost be similar, right? If the angle is small, the hypotenuse and adjacent side are nearly going to be the same. So that is why we kind of draw a perpendicular. We draw a perpendicular and then differentiate. So we have lambda. So sine theta is equal to lambda over A plus B. and this is central one. This is the brightest one in the center. Okay. Now, what is the condition required for this to be bright? Same thing. If that is to be bright, the path difference is supposed to be 2 lambda. So again, that is 0 path difference. That is half a lambda path difference. That is lambda path difference. So it's bright again. Not bright. Bright again. Like that. Okay? So when the path difference is 0, it's bright. When the path difference, is 0, it's bright. When the path difference is lambda over 2, it is dark. When the path difference is lambda, it is bright. When it is 1.5 lambda, it's dark. When it's 2 lambda, it's bright. That's how it goes. For the interference, that is the condition. So look at this. What makes this one bright? Sine theta, or a plus b sine theta is lambda. That's what makes this one bright. This is bright because of this condition. What is the condition for this brightness? So let me call this the 0th brightness. This is the first brightness. That's the second brightness. That's the third brightness. So what's the condition for the third brightness to exist? Sine theta is equal to 3 lambda over a plus b. So path difference is going to be 3 lambda. This is going to have a path difference of 3 lambda between these two rays. 3 lambda path difference will cause that. So it will be 0 right in the middle, dark, bright, dark, bright, dark, bright, depending on the path difference. You understand what is path difference, right? The path difference is the difference between this line from S1 to the screen and S2 to the screen. The path difference is the distance between them. And that's what we are trying to take as this path difference. If you keep going like this, the nth bright band will appear at what distance? Let's call it x. The nth bright band appears at a distance of x. Like this. So the light is going to travel like this, and from here all the way there. The path difference between these two is how many lambda? The nth brightness. For the third brightness, it is 3 lambda. For the fourth brightness, 4 lambda. For the nth brightness, it is n lambda. So that is going to be n lambda. The path difference is going to be n lambda. So for the green triangles, now if I draw a line from the center here to give you an idea of the angle, this angle is theta for the green. So what is sine theta? Sine theta is equal to n lambda over a plus b. N lambda over a plus b. That is going to be sine theta. Now look at this green triangle once again. Tan of this angle is xn divided by the d. Tan of this angle is opposite over adjacent d. So we have this. Sine of the angle is the path difference, which is n lambda over a plus b. Tan of the angle is the path difference, how much length is occupied on the screen by the nth brightness from the central brightness divided by d. So opposite over adjacent, right? Opposite or adjacent. Now, as I said, these slits are so close together. The angles that you're talking about is not like so big. They're all small angles. You saw that when I was projecting something on the screen. You know, you're talking about smaller angles there. It's not like big angles. So since you're talking about smaller angles, these two are equal. So if theta is small, sine theta is approximately equal to tan theta. And so you get xn over d, which is tan theta, what is that? N lambda over a plus b is equal to xn over d. So what is xn? Xn is going to be n lambda d over a plus b. So how far is the 20th bright band going to appear on the screen? Just put n as 20, put the wavelength, put the distance from the screen to there, and that is the spacing between the slits, and you get it. So if you want to know how far a certain bright band appears on the screen, that's simply what you do. Okay. So if the nth bright band is formed at that distance, where is the n plus 1th bright band formed? If the nth bright band is formed there, where is the n plus 1th bright band formed? So what do you do? Xn plus 1 will be what? What will be the change here? Lambda is not going to change, d is not going to change, a plus b is not going to change, just n changes to, so n plus 1 lambda d over a plus b. The distance from one bright band to the next bright band is called the bandwidth. Some books write it as x, some books write it as beta. Symbols are okay. But if you're calling it bandwidth, you can put any letter for it. Bandwidth is, what is bandwidth? It's a distance between successive bright bands. Bandwidth is the distance between two bands. Any two bands. It can be between the 10th one and the 11th one. It can be between the second one and the third one. Doesn't matter. That's why it can be between the n plus 1th one and the nth one. So what is the bandwidth? Subtract the two. So this bandwidth beta is xn plus 1 minus xn. Subtract. Because this distance from here to here is xn plus 1. And that this distance from here to here is xn. So subtract the 2, that will get you the bandwidth. Can you subtract the 2? Can you subtract this equation from this equation? And what do you end up getting? Subtract the two equations, and what do you get? If you open these brackets and then subtract, that'll make sense. Open the brackets and then subtract. So after you open the brackets, you'll have n lambda d over a plus b as one, and then there is a lambda d over a plus b is another one, right? So when you subtract, what do you end up? Lambda d over a plus b. That is the equation for bandwidth. That's the equation for bandwidth. How far apart are the bands? That's called bandwidth. Now, this a plus b can also be written as just d. The a plus b can also be written as d. D is what? D is the separation between the two slits. How far are the two slits apart? So, d. How is it d? Why is a plus b d? A plus b is the same as the center of this to the center of this. So it is basically a plus b. So from here to here, it is a plus b, right? From the center to the center, it is a plus b. So that is d. So you can also write that as beta is equal to lambda capital D over small d. as A plus B. So, when you use two slits, what exactly is happening? When you use two slits, you see diffraction, and in the area where diffraction allows light, you will see brightness and darkness and brightness and darkness and that sort of thing, and they are spaced by that much separation, which is called bandwidth. So you can actually figure that out. So if I tell you what's the color of the light that is being used, and you can figure out what should be the spacing. So if I'm going to use the laser from here, okay, if I'm using this laser, and if I put it to a double slit, and I show it through a double slit, the only thing we don't know about the double slit is the spacing. We don't know this, but we know everything else. The green's wavelength is known. Wavelength is known. The distance from here to the screen, known, right? This is known, that's known. Beta, you can measure the distance on the screen and find out how much is beta. So with that, we should be able to figure out what is really the spacing between this. How finely are those slits together? So Young's double slit sort of explains how interference is formed in the area where diffraction allows light. Okay? In the area where diffraction allows light, you are able to see interference as well. And I'll show it to you soon. In the area where diffraction allows light, you will see patterns of bright, dark, bright, dark, bright, dark, bright, dark patterns. And as I said earlier, this bright is not really bright, but this bright, which comes after that, is brighter. Why is this brighter? Because it falls in a extra brightness area according to diffraction. So diffraction allows light in certain places, and in those places you will see the interference to change in brightness. So the intensity of the bright and dark changes according to the availability of light, right? And what makes the light available is that gap A. The gap A is what makes the light available here and not available here according to this condition. Any questions on Young's double slit? Now this can be applied even for not necessarily light, sound. If I keep two speakers at a distance here, suppose I keep one speaker here, loudspeaker, another one here, 1 meter apart. If I keep two speakers 1 meter apart, connect both speakers to the same input source, like one source. One source. Why am I doing that? Well, why am I doing that? Because I want these two speakers to be coherent. Means the two speakers should be in phase, and the two speakers should be having the same wavelength and all that stuff, right? So if I keep one source, plug in one source into the two speakers and keep one wavelength, that means one frequency of sound, you should be able to see this brightness and darkness and brightness. But of course, since it is not light, it's sound, it will be loudness, less sound, loudness, less sound. So that's what you should see. So let me erase this. Okay, is that clear? You'll need to look back at this picture later on to get more information. Let me go back. All right. Using that equation, suppose I have two speakers, one here and one here, and both of them are connected to one source, which means they both have a frequency of, let's say, frequency is 500 hertz. Both have frequency of 500 hertz. And if both are turned on, if I'm going to walk here, so that's 1 meter away. And this distance from here to the screen, not a screen, basically this is the place where you're trying to test the intensities, that is 2 meters away. What are you supposed to listen at this point. Loud. So this will be loud, and here the sound fades away, and again loud, and again fades away, and you will see that. I mean, you'll hear that. Now, unfortunately, we can't do it in this room because of reflections. So you won't see, I mean, you cannot hear it distinctly. If you want to really test it out, we have to do it away from buildings. Best place, desert. If you go to a desert and then perform this as you walk by, you will hear clearly loud sound, literally nothing, loud again, literally nothing, that fluctuation. According to this. So tell me, how far apart are these? What's the bandwidth here for this question? What is bandwidth? Bandwidth is the distance between this loudness and that loudness. That is bandwidth. What's the bandwidth? What's the wavelength? You know, the speed of sound is 340 meters per second. Since it is not light, you need speed of sound, not speed of light. So what's the wavelength? Lambda is equal to 68 centimeters, which is 0.68 meters. So we have the lambda, we have the d, we have the small d, we have everything. What's the bandwidth? Lambda d over d, 0.68 times 2 divided by 1 is 1.36, right?
Yeah.
1.36 meters, that means what? If I'm standing here and right in the middle, it will be loud. You go 1.36 meters, it will be the next loud. That means if I go halfway down, what is halfway of 1.36? 0.68. So if I go 0.68, it will be literally no sound. Again 0.68, it will be loud. 0.68, no sound. So loud, no sound. So this gap is 1.36 meters. So what you hear is pretty much Young's interference pattern, but not light. It will be in the form of sound. Make sense? So this equation can be used for waves in general. It is not necessarily, it doesn't have to be only for light. It can be applied for even water waves. We can apply it for water waves. Ripples. If you create ripples from close by distances, suppose I create ripples from here, ripples, and ripples from here. That's a wavelength. And those two ripples will actually interfere and form maximum intensity here, maximum brightness, maximum amplitude, less, maximum, less. I think we discussed that last year, right? We discussed about interference with waves, and yeah. So on a ripple tank, you should be able to see those things. You can look it up online about ripple interference using ripples, and you will see those patterns, perfect patterns. The patterns will be like pretty much the same. All right, so when you use a double slit, what are you going to see on the screen is what I'm going to explain right now. All right. When you use double slits, what will you see on the screen? You will see intensity variations on the screen. You will see intensity variations on the screen like this. So that's your screen and that's the bottom line. So this is your intensity graph, sort of. So this is the center. So your you're going to have intensity variations like this, and goes on. So the intensity variations are going to be like that. Now, This pattern that you see right now is what? Caused by what? Diffraction. What's the condition for diffraction? What is this condition? A sine theta is equal to 0. What is that condition? A sine theta is equal to lambda. What is that one?
2.
Yep, good. And this happens on both sides. A sine theta is equal to lambda. A sine theta is equal to 2 lambda. And it goes on. Okay. So A sine theta is 2 lambda, A sine theta is lambda, A sine theta is 0. So these peaks appear according to this condition because A is what decides the pattern. Now when you use two slits, what are you going to see when you use two slits? When you're going to use two slits, you will see interference in the area that you end up seeing diffraction. So this is what you see. Okay. So what are these peaks that you see there? Those are the interference peaks, which means what? Bright, dark, bright, dark, bright, dark, bright, dark. That's stuff. What is the condition for this red peak, the interference peak? What's the condition for that? A plus B sine theta is equal to 0. The middle one. What is the condition for this? The next brightness. By the way, what is this gap supposed to be called? Bandwidth. Okay, so what is the condition that this will appear? A plus B sine theta is equal to lambda. And this is a darkness in between, which is according to the condition A plus B sine theta is lambda over 2. So this will be for lambda over 2, and that's for lambda. And this peak is for A plus B sine theta is equal to 2 lambda. And that one is A plus B sine theta is equal to 3 lambda, and goes on. Those are the interference peaks that you see here. So this is bright, this is bright, that is bright, and goes on. Bright, bright. And what is between the brights? Dark. Between the bright, it is supposed to be dark. Even though diffraction, the blue one is diffraction, right? Even though diffraction is saying, all right, use my light, but the interference kind of kills it and makes it no light there, or minimum. So even though diffraction allows light in that area, interference takes place and makes it dark. Make sense? Even though interference here is telling, all right, be constructive, but diffraction is not allowing enough light over there. So this constructive is not going to be as bright. Look at this one. This brightness is brighter than this. The reason why this one is brighter than this is because diffraction is allowing more light, because it's going to the second one. So you can see these bands, but the intensity of the bands are not uniformly going down. You can see that intensity goes down, goes down, goes down, again picks up a little bit, again goes down, again picks up a little bit. That's because of this diffraction envelope. So what exactly do you see on the screen? What exactly do you see on the screen? You don't see this blue line at all. So I'm going to take it off. You don't see the blue line at all. On the screen, you will see this. That is what you see on the screen. You don't see the whole thing. You see this pattern. And why is this pattern why is this brightness dimmer?
It's because it
Because it falls in the diffraction minimum area. Make sense? Why is this one, why is this brighter? It's because it is in the second diffraction peak. So you can see the pattern exactly. Even though I erased it, you can actually see the pattern. This is tall, goes down, again picks up, again goes down, again picks up. This is what you see on the screen. When this is done, this is pretty much what you see on the screen. And I think I showed this to you, but I thought you really wanted to know it. All right, now, if you use green light instead of red light, what's going to happen is the central peak will be here. That will be there. But this peak is not going to be here, but it will be more closer. Make sense? This peak is not going to be here. For the green, it will be closer. For the blue, it will be still closer, because blue's wavelength is smaller. And although I have this blue one, or green one that is, although I have this blue one, it is, the blue is not so easily sensed by your eyes. And so by the time it goes through this, it kind of, it's not good. It's not clear to your eyes. So you will, in fact, interference and all that is taking place, but since our cones don't receive blue as well as red color or green color, green is the best one. In fact, all the intensities are exactly the same, but this blue, look at that. It's hardly visible. And the green is the most visible, because that's the kind of a peak. Red is also not that good. Green is always well seen. I think even stoplights also from a distance, I think green will be more visible than the red. I think. Yes?
What about the yellow?
Yellow is also average color, so that also should be seen. Yellow-green is the best color for your eyes. All right, come back to this. So what is the condition that this takes place? A plus B sine theta is 0. This one takes place. This one is A plus B sine theta is lambda. A plus B sine theta is 2 lambda, 3 lambda, and so on. Those are the interference peaks, and you can see what's happening here, right? This is for how many slits? What will happen if there are more slits? Let's see 3 slits.
More interference, it gets lumpier.
Yeah, so I'm going to erase this, and I'll put all these things together.
Yeah, I'm not going to try.
All right.
I'll take a picture.
Take a picture with my mind. Now we're down to regular waters.
The next ones are easier to draw. So
Really?
Easier than
yes. So 3 slits. What happens if you use 3 slits? There are 3 slits like that, right? Now, these 2 are going to cause interference. These are also going to cause interference. But because there are interferences from here and from here and from here, what happens on the screen is intensities are kind of disturbed, but the disturbance is very orderly too. And this is what happens for 3 slits. For 3 slits, this is what you see on the screen. For 3 slits, this is what you see on the screen. Look at that. So what do you notice compared to the previous picture?
Lumpier.
No, these are still in the same place.
The peaks are different.
No, these peaks are still in the same spots as the previous one. But
As you go across.
as secondary starts popping in. So these are secondary peaks. You can see these are secondaries. These are the primary peaks. The primary peaks are still there. The secondary peaks between the primaries appear. So this is also primary. So these are the primaries, primary, the ones which you saw for double slit, the same thing. But what's happening is a secondary starts popping in between the two primaries. Now what will happen if you use 4 slits?
We're getting into madness over here.
If you use 4 slits, this is what the consequence is for 4 slits. What is noticed?
2 secondaries.
2 secondaries are coming in. When you have 5 slits.
3 secondaries.
The peaks,
Crazy.
Oh boy.
Crazy bit of gang.
that's what you see. How many secondaries? 3. And so tell me one connection, or what is the sequence that you see here? What is the pattern that you see? What do you see?
More secondary.
More secondaries.
If there are 5 slits, you get 2 less secondaries, correct? So if you use n slits, you have n minus 2 secondaries. What's the other thing that you notice?
The things get thinner.
Narrower. Look at this primary. The primary is getting narrower and narrower and narrower. What else do you see? What else do you see in this? So primaries are getting narrower. Secondaries are getting more in number.
Are they getting smaller?
Secondaries are getting smaller and smaller in intensity. Right? This is more intense. These are getting smaller, smaller. So if you use 1,000 slits,
It's a lot of secondaries.
if you use 1,000 slits, what will you see when you use 1,000 slits? The primaries are so narrow. The primaries are so narrow. You may have primaries here too. Okay, you may have primaries there also, but primaries are getting narrow. Secondaries, if there are 1,000 slits, how many secondaries are supposed to be there? 998 secondaries. But the other consequence is it is dimmer and dimmer, and for 1,000 slits, it's so dim that it is not even visible. Yeah.
You know those things where you can like put it up to your eye and look at a light and it shows like lines?
Yeah, we're going to see it. We're going to see it right now.
You're a genius.
All right. Do you see what's happening? Where are the secondaries? They are there, but it's so weak that you don't have to even see it. You cannot see it. So if you use 1,000 slits, then this is a consequence. You will not be able to see only, you can see the primaries, but you won't see anything else. So basically, even this blue line is not there, right? The blue line is not there. You won't see anything here. All you see is bright, bright again, bright, nothing else in between. It's just sharp. It'll be, so 1,000 slits. You want to see 1,000 slits? Here it is. 1,000 slits.
Oh, so they don't. Wait, are they all like in a line, or
You cannot see, how can you see
I was
1,000
gonna
slits
say
here?
like
are they in a line, or are they just like?
I don't know which way they are oriented as well, because when you cannot see, my eyes are anyway terrible.
so would you need a pretty big laser to shoot through all 1,000?
No, I'll show it with this one.
Oh, these are the double slits.
Yeah. You see the double slits getting narrower?
Wait, where are the door slips? Wow, wait, your fingerprints all over it.
So they're so close.
That was not.
So the last one I was. Those are double actually. But
Yeah.
can you see it?
can't
Double?
Yeah.
Oh wow, I cannot see.
Well, I can't see it, but I.
Oh, I see them.
You see them? You see them?
You see all 1,000 of them?
Now,
You want me to count them?
Count out.
all right. Now turn the. No, you don't have to. No, don't turn the lights off. Watch this now. I'm going to shoot this laser through the 1,000 slits. What you're supposed to see is this. Pay attention here. So when I put this here, look.
Whoa.
That's a peak, main peak. Then the next one comes here, and then so maybe I can merge with this. Yeah. See that? I can merge with my drawing. Turn the light off now. You see something more there? Oh my God, that's also merging perfectly. What? That's also merging. Yeah. It merges with the line I drew. I think I'm getting better at it. All right.
CM goes on.
Okay. So, oh yeah, turn the lights off. I'll show it on that. Here it is. Look at that. I don't know if you can see the other one. It's there?
Yeah, it truly did.
Wait, this is
Yeah.
Remember, you're gonna make a gap on a sunny day.
Was that?
You're gonna make a gap through the wind, through the blinds on a sunny day.
A gap?
What do you mean?
Yeah, yeah, we will do it.
We'll do it.
Yeah, we'll do it. Okay. Let it turn sunny. Now, what if I use green light?
Oh yeah, it's not sunny.
We'll do it. And it's
It'll be closer.
green light, what will happen? It'll be closer. Then you may be able to see more. Okay, so you look at that.
Whoa! Look over there.
You see one more extra, right?
Yeah.
Now the bandwidth is actually reduced, and so you should be able to see more of them. And let's put it on this one, on this place. See? It's supposed to be like this.
You can see one that's way far out. Like you can see them like your side down.
Yes, you'll see more. And with the blue one, it'll be still closer. With the blue one, it's still closer.
That hurts my eyes.
You see it? I know this color is kind of weird.
Yeah.
You can see how many bands are there. All right, settle down. Turn the lights on again. Now what if? So this is what you see here. What if? Oh well, let me finish off this equation part of it with this. So what is the condition? What is the condition for this one to appear? A plus b sine theta is equal to 0. What is for this one? A plus b sine theta, lambda. So this is a plus b, or I can just call it d, or a plus b. All right, a plus b sine theta is equal to lambda. This one is a plus b sine theta is equal to 2 lambda. And this number that you see here before the lambda, it's called the order. So this is a 0th order, that's a first order, a second order, it's the orders. They're all called orders. So 0th order, first order, second order, if it is available. Now you saw how many orders were visible, right? You saw less orders for red, more orders for green. So if you're using n slits, what is going to be happening is a plus b sine theta is equal to whatever order you're talking about, so m lambda. M stands for the order. M stands for the order. If m is 0, that means you're talking about this equation. If m is 1, you're talking about this one. If m is 2, you're talking about the second order. Right? Now let me look at this n slits. Let me draw all the n slits. All right, take this off. So this is A, then B, then again A, and then B, and goes on. How many A plus B's are there in 1 meter? How many A plus B's are there in 1 meter?
50.
Huh?
50.
50. No, not physically here. Do it algebraically. If A plus B is the distance occupied by one slit,
Oh, there's n minus 1.
how many slits are here? There are n slits in 1 meter. So what is n equal to? 1 over. If you divide 1 meter with the size of each slit, you will get 1 over A plus B, which is the number of slits. So, look at this equation. Sine theta is equal to m lambda over A plus B. So 1 over A plus B can be replaced with n and then lambda. This is called the diffraction formula. That equation is called the diffraction formula. Oh, grating, by the way. When you have n slits, it's called a diffraction grating. If you have n slits, it's called diffraction grating. Grating means like, lot of scratches. So how do they make this? They make this by taking a large scale drawing, and on the large scale drawing they draw lines, black lines, many of them. They draw a lot of black lines or print black lines, whatever, and after the black lines are done, they take a picture of that, and the negative of the picture will have transparent area, opaque area, transparent area, opaque area, and then shrink that thing into a smaller size, and then they put it between plastic. So it's like sandwiched between two sheets of plastic. So the slits are inside, which is basically a negative of a picture. So that's why it is so fine. And how many slits are here? Probably 1,000. So what is n standing for? N stands for number of slits per meter. So this one has 1,000 slits per centimeter. If it's got 1,000 slits per centimeter, how many per meter? What is n? 100,000. Do you get it? Is that clear?
Yeah.
So n. So once they make a particular grating, they will say how much is n. I don't know exactly how much is this, but it is in the thousands. I know that. So this, you can also find it out by measurements. You can actually find the angle at which that peak comes in. You can find the angle. So you know the angle. You know the angle. You know you're talking about the first order, and you can actually find out what wavelength of light was used, and you can figure out what is this, the number of slits per meter. We can figure that out. So that's called the diffraction grating formula. Diffraction grating formula, or just the grating formula. Now what will happen if I use white light instead of red or green or blue? What will happen if I use white light?
Separate.
Right in the middle, you're going to get white, because all the colors will be right there, right? The first order, what's this equation? Which color will have less angle of diffraction? Violet. So you'll have violet here and red here and green here. In other words, you have spectrum of colors. And on this side it's just the opposite. Violet here, green middle, and red far end. So if you use white light, you will see spectrum of colors here, and white will be right in the middle. And then you will see, if there's a second order, you will see that also. Make sense? So instead of seeing one color, you will see the colors of the rainbow, basically. It depends on how well it is done. So if I shine white light through this, not a single color, not a monochromatic source, but light, white light, then what will happen is you get the spectrum. Which color is diffracted the least? Which color is diffracted the least? Violet. Which color is refracted the most, or the least? Refracted, on the prism.
Red.
Red, what? Did I say least? Yeah, least, yeah. So red is refracted the least, violet is refracted the most. But here, violet is diffracted the least. Make sense? So here, violet is diffracted the least, red is diffracted the most because of its wavelength. Now I'm going to show you how those colors appear. So this gadget, what I'm having right now, is what he was describing probably. So I'm putting this. Now the grating is right there, not placed properly. Yeah, this is it. Okay. Now there's a tiny slit here. Can you see the slit? A tiny slit.
Yep.
So what we're going to do is we're going to point this to a source of light, white light, and then when you point it straight to a bulb, you will see this. You will see this. Right in the middle, it will be white. This will be white, and then you'll see the patterns on both sides. All right?
You can try. Jay, can try. Oh, okay.
Yeah. Try.
Oh, yeah, more. Oh,
Oh, fumble.
I wasn't ready. Oh, he's got multiple.
Whoa. What do you call these?
Now point. No, you have to look through the diffraction grating. Yes.
So we had the solar eclipse and it was staring.
Do you see the first order clearly? I think you can see the second order too a little bit.
Yeah.
Can you see the second order also?
Yeah, you can.
I don't know if mine has a
Barely.
Just
Mine
like-
just a little bit.
Just a little bit. Yes.